All right, so this is the dot diagram section. It may not be the same as your test, but I will try and go slow enough that I'm explaining how to do it again, so you know what to think about. So if we look at the SO3 here, you'd have 6 plus 6 times 3 to give us a total of 24 valence electrons. Sulfur in the middle, you'd set up your skeleton structure like this. Of the 24 valence electrons, now you have 6 in the picture because each of these lines counts as 2 electrons. That leaves us 18 electrons to put in as individual dots. So 24 minus 6 is 18 electrons as individual dots. Here we go, 1, 2, 3, 4, 5, 6. That makes 8 around the oxygen because these in the bond count as 2, both for the oxygen and for the sulfur. All right, I put 6 here and 6 here. And what that means is, where we are right now, is that every oxygen has 8 electrons around it. 2, 4, 6, 8. But the sulfur only has 6. 2, 4, 6. The idea behind bonding is that things want to have 8 in their outer shell. So they arrange themselves so that they do have 8 in most cases. A couple of exceptions, like hydrogen only gets 2, but because it's the first energy level is the outer shell and it only holds 2. But for most elements, you want 8 in the outer shell. So I'm going to take electrons off of the oxygen, and I could pick any oxygen, I'm just randomly picking this one, and putting in a double bond. So when I didn't have enough electrons to go around, what I had to do was share more. I needed 2 more than what I had to work with, so I have to share more. So now in the picture, if I did 24 and subtracted all the shared electrons, it'd be 24 minus 8, which would give us 16 dots. If you look here, do I have 16 dots? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, yes. And all of the elements have 8 electrons around them. So, see 2, 4, 6, 8 for the sulfur, 2, 4, 6, 8 for the oxygen. And the other 2 oxygens are like they were before. They still both have 8. Okay, the electron domain geometry, since there are 3 domains, here they are. We have domain number 1, domain number 2, domain number 3. There's 3 domains. That's called trigonal planar. The molecular geometry is the same when there are no unshared pairs. To figure that out, you need to refer to that little sheet. And the bond angle is going to be 120 degrees. The central atom formal charge is 2, and the reason we know that is because we've got 6 minus 6 for the sulfur. So half of the shared electrons, there are 2, 4, 6, 8 shared electrons, so 6 minus 4. There are no unshared electrons around the sulfur, so the formal charge is 2. Dipole moment, no, because the electrons are going to go this way, and that way toward the more electronegative element. So if these were forces, the sulfur would not be moving because you'd be pulling at equal distances from the sulfur, always out. All right, so dipole moment, no. Next one, CS2. You got 4, 6 times 2. So you've got 16 valence electrons. You set up your picture. You take away the electrons that are in the picture. So now you have 12 to put in. If I put 6 electrons here and 6 electrons here, you can see that I'm going to be fine for my sulfur, but I've used all my dots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I still need electrons for the carbon. How many more do I need that I do not have? I need 2 here and 2 here, because right now the carbon only has 4 electrons around it. So to deal with that, what you have to do is take out some of the electrons, and we'll put them back in the picture with double bonds. So remember, I was 4 short. Okay, so now I'm going to put in 2 double bonds. If you're 4 short, either put in a triple bond or 2 doubles. So I'm going to put in 2 doubles to keep it symmetrical. And now they're in the picture, I've got 16, but it's 16 minus 8, not minus 4 anymore, because I've got 2, 4, 6, 8 in the picture. 16 minus 8 gives us 8 to put in. So I have 8 electrons to put in. 1, 2, 3, 4, 5, 6, 7, 8. That satisfies the octet rule for everything. Sulfur, 2, 4, 6, 8. Carbon, 2, 4, 6, 8, and so on. So that's a two-domain situation. 1, 2. That's linear. And the molecular geometry is also called linear. Per that sheet, bond angle will be 180 because it's a straight line. Formal charge will be 0 because you have 4, right here, 4, minus half 2, 4, 6, 8. Half of that is 4 equals 0. There aren't any unshared pairs. So is it polar? No. Electrons would move toward the more electronegative element. And so, no. SO2. SO2 is 6 plus 6 times 2. So you've got 18 electrons to put in. Put the sulfur in the middle. Take away 4, you got 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Uh-oh, we're out of electrons. But I still need 2 for the oxygen. So I'm going to have to take off some electrons. And put in a double bond. So now I've got 18 minus 2, 4, 6 will give me 12. So 2, 4, 6, 8, 10, 11, 12. There's our picture. Now what happens is these electrons push down on that, and make the molecule actually do this. It bends. All right, so there are 3 domains. 1, 2, 3. So this is trigonal planar. And the molecular geometry, though, is called bent. And that's per the sheet. If you have one unshared domain, there's no atom up here, so we just say that the thing bends like this, bent. That makes a bond angle about 120. It won't be exactly that, but it's close. Formal charge on the center atom, let's see, we've got 6 for the sulfur, minus 2, 3, 4, 5. So 1 of each of the shared electrons. So that's 6 shared, half of that's 3, 4, 5. So 6 minus 5 equals positive 1. And is it polar? Yes, because what happens is the electrons move toward a more electronegative element. So they move in this direction and down in this direction. So they do not cancel. Those vectors do not cancel. And that makes it a polar molecule. H2O. H2O has a tetrahedral picture. So let's start. Count the valence electrons. 1 plus 1 plus 6 is 8. Take away 4. Gives us 4 to put in. So there'd be 4 domains. Here they are. 1, 2, 3, 4. 4 domains is tetrahedral. But since 2 of the domains are shared and 2 are unshared, we call that bent, because all we can really see, if we don't see the electrons when we look at the model, is a bent structure like that. The bond angles here should be a variation on 109.5, and what happens is the unshared pairs push down disproportionately. So it makes these guys smush in a little bit more than they would if it was 109.5, so they get a little bit closer together. It's just because the unshared pair is makes a big cloud. So you get this big cloud here and a big cloud back behind. It pushes everything together. Formal charge would be 0 because it's 6 valence electrons for the oxygen minus 1 of these, and then all 4 of the unshared. So it becomes 6 minus 2 minus 4 equals 0. And yes, it is extremely polar. Remember hydrogen bonding. It does exhibit hydrogen bonding. The NH3 has a central structure or a skeleton structure like that. It has 5 plus 1 times 3, which is 8 valence electrons. Take away 2 per bond. That leaves us 2 to put in. So 8 minus 6 equals 2. They have to go around the nitrogen because each hydrogen is already full, since the outer shell of hydrogen only holds 2 electrons. Domains are 1, 2, 3, 4 of them. So we say that's tetrahedral. But if there are three domains that are shared and one that's unshared, we call that pyramidal for the molecule. And the reason for that is it looks like a pyramid. You can kind of see it there. All right. And the bond angles would be about, there should be a variation on 109.5 because of the tetrahedron, but since this pair here is unshared, what it'll do is it spreads out a little bit like that, and that pushes these down a little tighter. The formal charge on the center atom is 5 minus one of each of these shared plus these two, so 5 minus 3 minus 2 is 0, and yes, it is polar because the vectors for the charge go toward the nitrogen, and they do not cancel each other out. Okay, H2C2 looks like this. The H's have to be on the ends because they can't be in the middle because you can only have one bond or 2 electrons on an H. Valence electrons would be 10. Take away 6 because there's 3 bonds there, gives us 4 to put in. If I put 1, 2, 3, 4 in, then I'm out of electrons. And everything's happy except for this carbon, which wants 4 more. So we're going to have to take out some of the electrons that we put in some more bonds. And if you're 4 short, you're either going to use a triple bond or 2 double bonds, but here it has to be a triple bond because you can't put a double bond on the hydrogen, obviously. So that gives us then 2, 4, 6, 8, 10 in the picture. 2 here, 4, 6, 8, 10. So that means we don't have any extra to put in, so it's 10 minus 10. So that's it, that's the whole picture. Okay, the domains on either carbon are 1, 2, so it's 2, so it's linear. It means the molecule is also going to be linear. Bond angle be 180 for a linear molecule. Formal charge, carbon is 4 minus one of these, one of these, one of these, and one of those. So half is shared, 8 shared, so 4 minus half of 8 is 4. And that gives us 0 for formal charge. And is it polar? Well, no. Because what's going to happen is that the vectors are going to go into the center toward the carbon, like that. And they cancel each other out. So it is not polar. Okay, the last one is XeF4. You've got 8 plus 7 times 4, which is 36 valence electrons. You put an Xe in the middle. You put the fluorines around it. Okay, of the 36, now I have 8, so I've got 28 to put in. So I put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I still have 4 more electrons that I haven't put in. Note, I am not 4 short. I have 4 too many. And if you have too many, the extra ones have to go around the center. You do not, I repeat, do not add double bonds. You put the extra ones around the center like that. So what that does, this pair of electrons spreads out a little bit. And this pair of electrons spreads out a little bit. So the best way for these electrons to get away from each other is to go into this square planar configuration. So the geometry has 8 domains, so we call that octahedral. Here they are, 1, 2, 3, 4. I'm sorry, 6 domains, not 8 domains. So it's octahedral with 6 domains. And 8 sides if you drew the picture of it, which is hard for me to do right here. If there are 4 shared and 2 unshared, 4 shared and 2 unshared, we call that a square planar. Because this right here is going to be a plane. That box there is all going to be flat in a plane. Bond angles all have to be 90 degrees in order to make that shape work. So between this bond and that bond, they're going to be 90 degrees to each other. The xenon, I've got so many scribbles here, it's hard to see it, but the xenon has 8 valence electrons, so you're going to take away 1 for each of these 4 bonds, so 8 minus 4. Then you're going to take away all the unshared, and there's 2 on top and 2 on the bottom, so 8 minus 4 gives us 0. And is it polar? Well, these guys are pointing out toward the corners of this plane, but they're all equally pointing out, and it's all flat. So it will not be polar because all those vectors are going to cancel each other out. All right, I think that's good. I was going to maybe try and draw this octahedral. So back, if you just want to see what octahedral looks like, maybe I can make it look like an octahedron here. The reason it's called octahedral with 6 domains, you got a pair up here, a pair down below. So you kind of visualize that all goes up, and then there'll be another one of those that comes down. So 1, 2, 3, and then the back side back here would be 4th side. Then there'll be 4 more on the bottom, and that's why it's called octahedral. All right, that's it.